shall I try it? Ferdi, you're muted.
Oops, I was about to say, Daniel, we are recording.
Perfect, thank you. No, doesn't sound as good as Neil.
No, I'm sorry.
Well, guys, this lecture is rather similar to the other one we had about input device. It starts with a definition of an output device and an overview of some output devices that we may use for our assignments or that you can use for your final project. This list or this lecture is not exhaustive. So if you have in mind a specific output device, please ask us and we can go deep maybe in analyzing it or try to use it.
So Ferdi knows how to make a fire maker, right?
So again, similar to the other definition of an input device, in our case, we define an output device as a device that can take as an input an electrical signal and that can give as outputs a change into the physical world. So in this case, the change into the physical world can be movement, can be light, can be temperature, can be colors, it can be sound, it can be anything that changes into the physical world. In this case, this input signal that we give to the output device allows us to finally control the output device. So this means of a model, we can change the speed. Of a display, we can change the colors and the image. Of a speaker, we can change the sound, finally change the sound, the speed, and so on. So we start with a very simple output device, which is the speaker. I think that almost all of you know what a speaker is. In this case, it's possible to use directly a speaker connecting it to the microcontroller. Of course, guys, the microcontroller doesn't have a lot of computational power. So if you use some kind of simple libraries or kind of simple signals, you can just play some simple music on a speaker. This will sound like the 8-bit ringtones that we have in our smartphones, or like very old, like video games, music. In this case, with the addition of some additional devices, for example, MP3 player chip, then what you could do is you can even play standard MP3 music, or you can like synthesize voice and so on. But this is something that cannot be done straight from the microcontroller. You need some additional chip to it. Of course, light emitting diodes, you already have been using those in your boards, I believe. You also have one inside the Arduino. So with the LEDs, you can have, of course, like one single LED. You can have a set of a group of LEDs. So you can have like LED strips, or in this case, like LED matrix, or like LED placed in a three-dimensional space. And then every LED can have a specific color and light intensity specifications and so on. But of course, you can also have LEDs that they can express the whole range of colors. For example, red, green, and blue LEDs. In this case, these LEDs is like that they have 3 small LEDs. Inside, one red LED, green LED, and blue LED. Yes, William, I was accepting you. You are too late in the first one.
It's a question I wanted to ask Neil actually on Wednesday, but I didn't get quite fast enough to open the mic. Those things are essentially 3 LEDs together, right? They're a red, a green, and a blue together in the same. Yeah. Do you get to? Can you, with one of those things, can you get intermediate colors by changing the intensity of each one of the components? Does that work?
Yes, you can change the intensity of each of those LEDs, and then you can mix the colors, basically.
So can you? Okay, that's what I was wondering whether you could do that. Thanks.
Of course, because you have 3 small LEDs inside, it's not that you have only 2 connections, like anode and cathode of the traditional
No, you have
LEDs.
That's right. So you have 1 plus 3 or something. Right?
Yes, you have 4 connections. three for the diodes and one common. It can be positive or negative, anode or cathode, according to the configuration.
So in my car stereo has one that goes between blue, red, and then it does purple, and it does other things. So is that what it's doing? Is it taking one of these 3-pole things and changing the relative PWM, or are there LEDs in other colors?
No, it's changing the PWM for each single LED that you have inside. So each LED
mixing the color.
PWM
Okay.
color, yeah, and PWM signal, sorry, and then changing this signal, you can change the color. So there are some LEDs that will just like variate along all the range, or some LEDs that are managed by an additional microcontroller. As you may remember, for the input, some input or output device that could have electronics inside. So if there is a chip attached to these LEDs, maybe you don't need the fork connection to drive it. You need maybe I2C or some other protocol to communicate, like the NeoPixels, for example. Okay, but usually the bare metal RGB LED is just 3 RGB LEDs inside. Sorry, 3 LEDs inside, one red, one green, and one blue. And then you drive each of those individually.
And with those components, you can make almost any color. So, okay, cool. Thanks.
Yeah. Then, of course, you have more complex output devices that embed, again, as I was telling you before, some electronics inside. This is the case of a printer, if you think about it. So you might need to use a networking protocol to send the data to the printer, and then the printer will have inside its own controller, its own motor, its own ink cartridge, and so on, and then print something on paper. This kind of printer that you see here on the screen is like a shield for the Arduino. So this means that can be interfaced directly with a microcontroller. Of course, like computer printers, they use much more complex communication protocol and other kind of connections like USB and so on. So then this is something I think worth to mention. We have the shape memory alloy, that is a specific kind of metallic alloy that can change its shape. It can memorize a shape, and it can, let's say, replicate that shape if some conditions are going to be applied. In our case, the conditions are like specific amount of current and voltage that can be applied on the side of the shape memory alloy. The issue we had with those is that the one that we can find in the market, they usually take a lot of current, and they can apply really little force to retake the shape, if you think about this spring over here and so on. However, the last time with Ferdi, we had a nice discussion with a local company that had a very nice example of shape memory alloy. So these ones I'll be using for some nice experiments. For example, if you think about origami bird, you can like make the wings moving up and down with this shape memory alloy. There were several considerations about using it like in a glove, and then according to how you supply energy to the shape memory alloy, like open and close the glove and so on. So displays, we have a lot of different kind of displays. The display can be categorized by, for example, color display or just grayscale display. We also have only character displays or graphic displays. We will see some of this in the next slides. So with the display, you have the same consideration you have, for example, for the MP3 or for the printer. I mean, with the microcontroller, you cannot really have a lot of computational power. So there exists some displays that can be just, for example, having the LED, having the pixels on or off, like this one that is displayed over here. And then they are going to have usually like less refresh rates than the traditional displays that you have, and of course, much less pixels. Some of these displays, however, they have a chip attached to them, and this allows the microcontroller to communicate in an easy way, for example, with less connections, with less pins. Also, some chips can take care of the graphics of the display. So therefore, even if you use a microcontroller, you can have maybe colors and better resolution or graphics. So then we have all kind of motors, electrical motors. I believe that some of you already tried to work maybe with the servo motor or the DC motor that we have. So we will start giving some information about the simplest motor that you could have, which is the direct current motor or DC motor. This is also called sometimes brushed motors, because the principle is that inside there are some brushes, and these are used to transmit the electricity to the rotor inside. I don't know, here in the camera there is one, and you can see like there is a small hole in this one, and here you can see a little bit of the brushes and the rotor inside. So the principle of working of all the electrical motor is rather simple. You have basically magnets on the outside, and then you have coils on the inside, and the inside part is rotating. And according to the current that circulates in the coils inside the motor, this will generate a magnetic field that will interact with the magnetic field of the outer magnets, and then this will let the rotor to turn. So the DC motor is the simplest kind of motor that you can have in your project. The advantage of this motor is that is very cheap, and the disadvantage is that you cannot control it very precisely. So what you could do is you can control roughly the speed of the rotation of the shaft by varying, for example, the voltage that you apply to the pole of the motor. So this motor is recommended in case you have a project where you need to turn something, but you don't need to be, let's say, really precise in controlling the speed of the rotation. And as well, these motors are not the most powerful motors, so maybe you don't need even a lot of force to be applied. Think about like the RC toy cars, or think about like if you have to rotate a fan or something that has just to rotate without too much of control and too much power. So then other kind of motors that you can see on the screen are servo motors and stepper motors. I believe again that almost all of you already have worked with some of those. So in case of the servo motors and the stepper motor, what changes is that you can finally control the rotation of the shaft. So by this possibility of controlling the position of the shaft, you can enable a lot of different applications. For instance, all the digital fabrication machines that we have in our Fab Lab, such as 3D printers, laser cutters, and CNC machine, and so on, they use this precise positioning of the shaft, in this case of the stepper motor, to determine the position of the machine, or to determine, for example, what's the distance that one axis has to move to 3D print or to laser cut or to CNC mill something. Thanks to this positioning, then the machines are able to produce something precise. So a stepper motor is called like this because it works in steps. So this means that the shaft can rotate a certain amount of steps to make a full revolution. So usually when you buy a stepper motor like this one that you see in the camera, it has 200 steps per revolution. So this means that you have around 1.8 degrees in 360 degrees. So every step is 1.8 degrees rotating the shaft. And then according to the number of steps that you send from the microcontroller, like the command, okay, make 500 steps, 200 steps, and so on, then you can move or rotate something precisely. One characteristic of the stepper motors is that it has a lot of torque since the beginning. So from very low speed, it has a lot of torque. So it can move, let's say, heavy loads from slower speed. A drawback of this motor is that the faster it rotates, the more torque it loses. So it cannot rotate very fast, first, and second is the faster you rotate, the less torque you're going to have. And so one of the main difference between stepper motor and servo motor is that the servo motor, coming in this small shape that you see here on the screen, or like this one that you see here in the camera, is that it can rotate a specific amount of degrees. So usually these ones, the small one that you can buy, they will rotate by a maximum of 180 degrees. So you have this limitation, like from here to here, for example. The difference is that the servo motor will not work in steps. So you can finally move the shaft to any angle you want. It can be 55.63 degrees, for example. In that case, the comparison with the stepper motor is that you can just approximate that positioning with the number of steps, let's say. Then if you have more powerful servo motors, like some digital fabrication machines, especially big ones, they use high power servo motors. Then these servo motors can rotate 360 degrees, the shaft, and they also will have very good torque at higher rotation speed, so the high rotation speed, so they can go rather fast. The problem is that they will not have a lot of torque at lower speed. I mean, I'm talking about these big ones for the machines. So these big servo motors are used when you need a lot of speed and a lot of power at high speed. And this is the case, for example, of the X-axis of our Epilog Fusion laser cutter. So in that machine, to move the X-axis very fast in engraving, we have a servo motor instead of a stepper motor. Also, big CNC machines are coming with big servo motors nowadays in comparison to traditional stepper motors.
Daniel, I have one question about that. You just mentioned that the servo motor can only do 180 degrees.
Only the small ones. The small ones that you see, like this one on the picture, can do 180 degrees. But if you take like a big one, it can do 360 degrees rotation.
But what would I, where would I use that for? I mean, it's like just flipping a flag back and forth. I mean, I cannot move something really continuously, right?
Yes. So some servo motor, even with this small package, they come with 360 degrees. But this is something like a special feature, let's say, of these small ones. You can use those to actuate all kind of small systems that they don't need full rotation. So I give you a simple example. We made a plotter in our Fab Academy, when I did Fab Academy, and we needed a pen to just go up and down. Just this movement, you know? So we didn't need to have full rotation. We needed something that was going, you know, up and down. When you need something that doesn't require a really long motion, or like something that requires a very simple motion. It can be like a, you know, like a vending machine that opens and closes the bottom like a product pass. You know, something that needs to be actuated in a precise way, but maybe that doesn't have a lot of motion. They usually use this in these walking robots, for example. These spider walking robots, where the leg has to do a limited movement. But then if you go with the bigger servo motors, actually they can do, of course, 360 degrees, and yeah.
Okay, thank you.
So the last motor that we haven't mentioned is the brushless motor. I have also here a brushless motor. I don't know if you can see it in the cam. The main difference between this and the other motor is that this, the brushless motor, as the name says, doesn't have any brush inside like the DC motor. So this means that the stator and the rotor, they are not touching each other. The complexity that this creates inside the construction of the motor generates the needs to have different signals for each of the coil of the motor. because you don't have the brush inside, that they change the direction of the flow of the current in order to keep the motor rotating. So for doing that, you have actually 3 different signals. So you have 3 cables going inside the motor. And to generate this signal, you need to have a specific motor controller that is rather complex. It has a microcontroller on board and a set of MOSFET, which is called the electronic speed controller. So the brushless motor can be controlled very precisely in speed and also in rotation according to the construction of the brushless motor itself. And it's actually the most powerful motor among all the motors that we have introduced. So these motors are usually the ones used in drones, in electrical car, electrical scooter, in every situation where you need a lot of power and lightweight, you use a brushless motor. And also these motors are among the most expensive motors that you can find among the motors that I have presented in this slide.
What about torque at low RPM or relatively low RPM? So for my final project idea.
Depends also on the construction of the motor itself, because some motors are made to express the maximum torque at a certain rotation speed. Some other motors can have some torque at a really low speed, or from stop, let's say. So this one from drones, for example, I will tell you, I can almost like blocking them by hand when they start rotating, because they're made to have the maximum torque at the time speed of the propeller, you know. Then there are some other motors that can have good torque also since the start. We need to look the specification of the motor. So in your case, we can try to look the motor that you already have found inside the frame of the DPV, and see actually what are the specifications on that one, and then try to find something. Yeah. A lot of work also since the beginning. Okay, so this list is not exhaustive. There are a lot of other kind of output device, but covers some kind of, let's say, generic needs for your project. I think all of you should have a display and a servo motor, and also some LEDs and the speaker as well in your kit. So the output device, they need a specific signal to be driven. And according to the kind of output device, you have a different signal. So just to give you some insights about how you could drive some of this output device, in this slide, for example, in this image over here, we can see some signals that are needed to drive stepper motors. So to drive stepper motors, logically, what we need is to have this kind of square wave here. So you need to have a signal high for a certain amount of time, and then a signal low for the same amount of time, and then again the signal high for a certain amount of time, the signal low for, and so on. So every time that you have one of these combination here, so high and low, when the signal switches from high to low or from low to high, what you have is you have one single step on the shaft of the stepper motor. So then controlling the speed of this or the time of this one, then you have faster or lower speed in the rotation of the motor. So let's say again your motor requires 1.8 degrees for each step. So this means 200 degrees so 200 steps to do a full rotation. So to do a full rotation, you need to send 200 of these waves of this square wave over here to make the motor rotating. So with some advancement in the electronics, what we are nowadays able to do is to divide the hardware step declared for the manufacturer of the stepper motor into sub-steps. So this means that we can achieve actually higher resolution, or we can have more steps per revolution. So this, they are called micro-stepping operations for the stepper motors, and today they can reach up to 1/256 steps. So this means that you have not anymore 200 steps per rotation, but you have 200 times 256, for example, number of steps per rotation. So if you make it simple, maybe with the half step rotation, this means that from each step you have 2 steps. So this means that from 200 steps per rotation, you can have 400 steps per rotation. So usually in many of the 3D printers, or also the machine that I'm making here at home, the microstepping resolution that I'm using is 1/16. So this means that we can make 200 times 16 number of steps. So this means 3,200 steps per rotation. And then this combined with the different kind of gears, pulley or whatever you use to move your system, it results in a different resolution of your system. So this is the way that you drive the stepper motors. So then the way that you drive the servo motors, or the way that you also drive the brushless motor, or a transistor that drives a DC motor, is to use a pulse width modulation. We have seen this signal before in input device. So in this case, to have a different positioning of the servo motor, like 0 degrees, 90 degrees, or 180 degrees, what you do is you change the length of the pulse over here. So usually this is some kind of standard that also works for the brushless motor. This pulse duration goes from 1 millisecond to 2 milliseconds. So this usually means like the lowest speed or the 0 degree position is 1 millisecond. The maximum speed or 180 degree position is the pulse of 2 milliseconds. So you don't have to be scared about generating a pulse width modulation signal, because of course there are libraries that can do this for you. And what you have to do is you have just to put inside the call of the function for the library the amount of milliseconds that you want. So you can finally tune this according to your needs. So, and then of course some devices.
Sorry for interrupting. Did I get it right? Does it mean that 1 millisecond is always the minimum pulse and 2 milliseconds is always the maximum pulse, or is it just in this example?
This is some kind of standard that works almost in all the motor controllers, and like it's some kind of standard for all the producers of the motor controllers.
That means it doesn't matter if I have a brushless motor or a DC motor. If the pulse is 1 millisecond, the motor stands still, and if the pulse is 2 milliseconds, it spins at the full RPM. So
this one, no, not for DC motors, because with DC motors you need to use a transistor, and then this depends on the characteristic of the transistor. I'm talking about brushless motors in this case and servo motors. So servo motors means that this will be in 0 degrees, and brushless motors most likely this means it doesn't spin or it's stopped 1,000, 2,000 or 2 milliseconds, sorry, means that it's 180. So I will tell you, for example, in the drone, it's like this. In the big brushless motor that we use for the project from Karsten, that he made a scooter, electrical scooter, it's like this. 1 millisecond is not spinning. 2 milliseconds is the maximum speed. So for brushless motor, it's almost, let's say, standard. It's not exactly a standard in a way like the Deutsch norm or whatever, but if you plug it to a brushless motor, it will mostly have like that. And the servo motor, of course, will be from 0 degrees to 180 degrees. Yeah. So then, of course, some other devices can take a digital signal or an analog signal, and so on. This you might need to consider yourself the kind of device that you're going to use. Sorry,
Daniele,
yeah.
Can I interrupt? You say, and your graph shows the pulse width as 2 milliseconds. What's the repetition frequency? So the thing is on for 2 or for less than 1 millisecond, right? But then what's the time between one and the next? Or does that matter?
This one, in this case, it doesn't matter much. So what you do is you take the falling down or the raising up. In this case, you take the falling down. So what you say is from when the signal is high, now you measure this one, now you go down, and so on. So you can take the raising up, let's say from here, or the falling down from here. So this.
Yeah, sure, but that's okay. But the motor. So do I need always to send a pulse train, or do I send a single pulse?
No, you need to send a series of pulses, of course. Yeah, it's continuous. When the wave is not anymore a wave, it's all zero, for example. It's stopped.
Yeah.
So with the duration of the pulse, you define the speed. But then if you have no wave, you are not doing anything. In this case, with the motor, if it's flat line, the motor will not move. So, but in this case, guys, you can generate this if you want by yourself with the software, but it's going to be, let's say, rather hard. You need to work with hardware timers and so on. So in this case, what you could do is just use a library. For example, for the Arduino, we have analog write library, and then it will generate for you the correct pulse for your motor. So analog signal, we have an issue, which is you cannot generate an analog signal as an output with our AVR microcontrollers. With a newer microcontroller, you could do that in case you wish. But with the analog signal, you can drive some devices, of course. Whenever you cannot do the analog signal as output, you can use again a PWM signal, pulse width modulation signal, to simulate somehow the output of analog signal. This is the case, for example, of driving a transistor, because a transistor can be driven by the analog signal or by a pulse width modulation signal, which is mostly our case whenever we have our microcontroller that cannot output pulse width an analog signal as outputs. So it is forced to use the pulse width modulation signal. Further questions, guys? Okay, thank you. So I think Neil mentioned it as first thing, safety. The reason is that many of these devices that you're going to use, they cannot be powered directly from the microcontroller. So the microcontroller is built for logic. So this means it cannot deal with a lot of power. In this case, it cannot deal with high currents or either high voltage. If we see the specification of the ATmega 328P, which is the chip that powers the Arduino that you have in your kits, or to the AVR chips like the ATtinies that we're using in our FabSP and so on, this one can output maximum around 40 milliamps. And you know that many of these devices that we're going to use, especially the motors, they will take amps, not milliamps. So what you need is to have an external power supply that can give you enough power to operate your output device. This external power supply can even be a battery, can be a bench power supply that you can finally change and tune the power, so that the current and the voltage, or it can be something that is fixed, giving you a certain amount of power that you can use for your specific application. So how do you know how much current or how much voltage do you need for your output device? You have to go to the datasheet of your device, and then inside the datasheet, they are going to tell you which one is the nominal voltage and the nominal current that you need. So for example, this one over here, you have a series of current and voltages. You can also have some graphs over here, for example, that explain you like how much will be the current or the voltage according to certain amount of speed. So order, bring to front. So you can see here, for example, this graph over here with the torque and the current over here, speed and current. And then here you can see the specification. Okay, the voltage must be 12 volts, and this is the torque that you have, and the current taken will be 0.42 amps, which means 420 milliamps. This is the rotational speed that you're going to have, and so on. If you have load, no load, and so on. So please have a look to your data sheet according to check which power supply do you need for your project. An important thing that, as Neil mentioned, is that you have to take care that, of course, you don't get in touch with this higher amount of voltage or higher amount of current with your body, and that this system is somehow separated from the logic system that you have for your microcontroller. So if you supply the same voltage or the same current, of course, to the microcontroller, you can easily blown up, because we know that the FWAR that we use, they work with maximum 5.5 volts. So if you connect 12 volts or 24 volts, the microcontroller is going to blown up. So you can make a separate circuit for that to make sure that your device is powered by that, and your microcontroller is powered by something else. So in this case, something that you can do is power everything from one main source. So is the case, for example, maybe William of your Spider robots, or Hannes of your DPV system. So therefore, what you could do is you can then transform this input energy source to the voltage that you need to power the microcontroller. In this case, you can use, I don't know, a step-down voltage regulator, voltage dividers, and according to the current onto the voltage that you need. So the power supply is one of the devices that we need to drive our output device. But then we also may need another device in between, especially for the motors, or for devices that they work in a different voltage or with different current from the microcontrollers. And in this slide, we have a range of those. So we can call those like drivers. Inside this category, we have very complex devices, or even very simple ones, like the relays. And everything depends on what you want to drive. So we will start from the simplest one, which is the relay. So the relay is just a controlled switch. You have basically electromagnetic coil that will open and close a switch. And this coil can be driven from a microcontroller, for example. And then this switch, these two connections, can drive a much higher load. So if you see, for example, this one, it can drive a load that is 10 ampere, 250 volts alternating current. So this means 2,500 watts of load, for example. So there are some nice models where you can have the relays like this here. I don't know if you can see the camera. And with the relay, guys, what you have is just on and off switch. So this will be helpful if you want to switch on or off, for example, a huge flashlight, or switch on and off a DC motor, for example, but a fixed speed, of course. William, what's the question?
I think the one in your slide is if I've understood, that's a solid state relay, and the one you're showing us is a mechanical relay. Can that be? Is that true?
Actually, they are both mechanical relays. This one.
Oh, are they? Okay.
Yeah.
Right. So my question around the solid state ones, the mechanical ones, I understand it's a coil and you just move a switch. So there's an actual mechanical switch that moves up or down according to the magnetic coil.
Yeah.
So there's a complete isolation of the coil voltage from the switched voltage.
Yes.
Am I right on my understanding that that's not the case in a solid state one, that the two circuits are not completely independent one of the other?
They are not isolated the same way that you have in the solid mechanical relay, because the mechanical relay, they are just like, there is a space in between. And this space is usually like in void or something, or some kind of isolating thing that will never allow the coil to touch, of course, the other circuit. They are not proposed to protect the device that controls from the things that are being controlled. In the solid relay, I use them, for example, to drive the heaters of my big printer. Actually, the electronics inside is rather similar to a giant MOSFET.
That's what I wondered. Okay.
Yes, that's it. And the advantage is that some of these solid-state relays are just like having the name of a solid-state relays, but they are giant MOSFETs, so you can control all the status in between, even from on and off. Some of these solid-state relay, you can just use them as giant MOSFETs. So you can say 50% of the power, 60% of the power, and so on. So there is another advantage, of course. I mean, the mechanical relay, you have these mechanical parts that they have to click. And you know, they have a limited number. It's very high, of course, like maybe thousands that can go on and off. But this is not happening, for example, with a solid-state relay. So there are pros and cons in all of these different approaches. So the solid-state relay, because they act as MOSFET, they also have sometimes huge heat sinks, because they can do 50% of the power, for example, 60% is on, and they have to dissipate a lot of power. But the controlling mechanism remains the same. So if you send a specific signal to the relay, which is usually like logic level high, the relay will trigger. Logic level low, the relay will not trigger. In this case, for example, that this board that I have here, you have to check your relays, guys. So some very simple and basic relays can be driven directly from the microcontroller, but some relays, because they have the coil inside, the coil needs to have current that flows to generate a magnetic field to switch the circuit, and this coil can take some time more current than the microcontroller can give you. So what you do is you use a transistor, like this small guy over here, to then give more power to the coil of the relay, and you drive the transistor with the PWM for the microcontroller. So it's like chaining the transistor and the relay together. Sometimes you also have additional security things, like you have diodes here, opto-isolators over here, and so on, depending on the kind of relay. If the isolation inside the relay is not so good, you can also use opto-isolators. So just small thing to mention about opto-isolators, they are like having a LED inside. Here there are more opto-isolators. With a microcontroller, you can power a LED that is inside. This LED will emit light. This light will be received from a receiver inside the chip, and this receiver will open and close like a circuit and give the signal. So it's a way of letting the signal passing through it, but never like coming back, with kilovolts of isolation. So this is, for example, used when you have something on the other side, on the after the signal that you need to control, that can explode or can, I don't know, give you back a bad signal to the opto-isolators. So then if we go a little bit more complex, or we talk about more the solid-state relays and so on, we have, of course, all kind of transistors, MOSFETs that you can use to drive your motors. In this case, the next step is that you don't have anymore only on and off, but with the transistor or the MOSFETs, you have all range of power. So you want to say, okay, I want to power my motor at 5% of power, 10%, 20, up to 100, you can fine tune it. This that you see on the screen is a very common IC. It is an array of transistors inside. In this case, is the kind of transistor is Darlington transistor. So you can find even chips where you have, for example, in this case, 7 transistors inside as a convenience to drive other loads. So in this case, so one is on and off. The other one is varying the power that you can output. But we are still talking about very simple signal. So in this case, it's just high or low. In this case, it's just, let's say, an analog output signal that you have after the transistor that variates, for example, the voltage. So from 3 volts to 6 volts and all the range in between. Now, what if you need more complex signals like the one from the stepper motor in order to drive it? Then in this case, you have dedicated devices which are the stepper drivers. So in this case, this one is a small stepper driver from Pololu that is usually used to drive this kind of format, NEMA 17, this small format stepper motors that you find in all the printers and so on. Then you also have a bigger stepper drivers over here that can drive bigger format motor. For example, the NEMA 23 motors or the NEMA 34 motors, NEMA 42, and so on. One thing that is worth to mention is that inside the stepper driver, the basic mechanism that allows you to generate this kind of signal, high or low over here, is called the H-bridge. So you can have H-bridge as a separate component, like this L298 is H-bridge. And then you can create your own stepper drivers with this, adding interface logic to the microcontroller, adding capacitors, adding diodes for protection, optoisolators, and so on. So what I want to say is that the H-bridge is actually the core of the stepper drivers that you have over here. And the stepper drivers are just H-bridges with some other nice additions around them. So, and in this case, the stepper driver is dimensioned by the amount of current and voltage that can give to your motor. So usually these ones are in a range of few amps. So I think this one it's maximum 2 amps, while these big ones can go up to 4 amps or more, according to the current that you need for your stepper motor. The last one that is even more complex than the stepper driver for the stepper motor is the electronic speed controller. Here you have an example of it. The electronic speed controller outputs 3 signals that you need to power the coil of the brushless motor in a different order to keep the brushless motor rotating properly. And for this, inside this small package that you see here, you have a microcontroller that takes as an input a pulse width modulation signal, and that drives a set of MOSFETs to generate this kind of 3 different signals for the coils of the brushless motor. So this electronic speed controller are usually used in drones or everywhere you have the brushless motor, and they take as an input a pulse width modulation signal, and they also have as an input the power from the power supply. So you have these 2 big cables, like this black and red cable that are coming for the power, and then you have this white, red, and black cable over here, which is one is for the pulse width modulation signal, and then ground is to share the ground, and this red one is sometime in some electronic speed controllers or ESCs a step down voltage regulator. So sometime in some electronic speed controller, you have the advantage to have integrated step down voltage regulator. So this means that the electronic speed controller can give power to your microcontroller or to the logic of your project. So in the case, for example, of you, Hannes, for your DPV, it's possible that if we have to use a brushless motor, we use electronic speed controller with a step-down voltage regulator inside. Therefore, we don't need anymore any step-down voltage regulator. In this case, it's written here. It's called back. And then if you have the back, this gives you here, for example, 2 ampere, 5 volts of output in the step-down voltage regulator.
Oh, I just realized that I need to unmute to talk, but yeah, okay, I got it, yeah.
Okay. So you have questions about the drivers, guys? Okay, I think we can go on then. So the lecture now falls into specific cases.
Me too. I also need to learn how to hit mute. These are for stepper motors. The servo motors we control. So that you showed us for brushless motor. You show us for a servo motor, and for the DC motor, you haven't shown us here a controller for a DC motor.
For a DC motor, you can use a relay just for fixed speed, or you can use a transistor or a MOSFET.
Now, do I use a PWM for that, or I just adjust the voltage that goes to the DC motor?
The voltage is going to be adjusted from the transistor or the MOSFET, and the transistor or the MOSFET takes as an input the pulse width modulation, the PWM.
So I run the PWM into my transistor, which is then switching at the same speed. So essentially, I'm switching a high voltage PWM, right?
You have to input a PWM signal. Is actually this schema that you see here to the transistor, and then the transistor will variate its own internal resistance to variate the voltage. So
that's not a transistor anymore. Then that's some kind of circuit in there, is it?
It's the way that the transistor. So when you drive the transistor, maybe you have to go back to the transistor and electronics design. We have this thing that you can open, a little bit, half of it, all of it, and so on.
Yeah, it's a valve. Yeah.
Yeah, it's
and
like.
So that's right. So you vary the base to collector, or the base to emitter voltage, and that changes a valve.
Yeah.
Right.
But what you output is what the DC motor takes as an input to work.
Yeah.
Is not a pulse width modulation signal. It's an analog.
No. Right.
It's an analog voltage. Yeah. So you use the PWM just to drive the transistor. I think maybe the servo motor guys, the small ones, if this is not clear, the small servo motor, like these sides, can be driven directly with less than 40 milliamps usually from your microcontroller. But if you have a big servo motor, then you have a specific driver. And this driver, guys, it generates the specific signal according to also the specific servo motor that you have. So outside, they look similar to these ones over here, but they are much more complex. And they can vary the way that they work according to the kind of servo motor that you have. So for the small servo motor, guys, you don't need any driver. For the big ones, you need specific driver, similar to this one in shape, but with different ways of working according to the servo motor that you want to drive. So DC motors, so there are some simple examples now that you can check yourself. Maybe, hopefully, with some of those, you can try them out at home. And in this case, the one shown in the slide will allow you to drive a DC motor. And the circuit is rather simple. So you have from one side the microcontroller that can generate a pulse width modulation signal. In fact, is connected to a PWM pin number 3, for example. And then this resistor here depends on the kind of transistor that you're going to use. You might need to have a different voltage than 5 volts, for example. Then you put a resistor here to change the voltage that goes to the gate. And then the other two, the collector and emitter, are connected to the main power. As you can see here, the ground is shared between the microcontroller and the GND. This GND outside comes from a battery or an Xenophore supply. But the positive voltage that goes here is not shared. It comes directly from the outside here. So basically, the transistor here is like a valve, as William said, that can be open and closed according to the PWM that you have here in the gate. So when the PWM is high enough or low enough according to the transistor, this valve can be completely open or completely closed. If it's completely open, the motor will rotate full speed, so you have maybe 6 volts. If it's open half, you have 3 volts, and so forth for all the ranges in between. So the connection looks rather simple here. Because of the current that can pass in the MOSFET or in the transistor, here, guys, you have a heatsink. sometimes this device can even melt or burn down if you don't provide enough cooling. So in the datasheet, you find information about the MOSFET or the transistor heatsink. Some of this device can take a huge amount of amps. So we are talking about hundreds of amps, only if they have the proper cooling. If you have ever opened a power supply from a PC, for example, you will see giant heatsinks inside those. So this hole here, you attach a screw, you screw it to a giant heatsink. So let's have a look to the code. So it's obvious now that the pin that you want to use must be set as output pin because you want to output a pulse width modulation signal. So you define the motor pin here, number 3. You declare it as output. And then inside here, you use the analog write function from the Arduino. This analog write function from the Arduino allows you, although the name is quite different, it allows you to output the pulse width modulation signal. William.
Okay, that's what I was going to ask. Because analog write, that's not putting out so I'm writing analog write to a digital port.
Yeah, you're right.
That's where I'm getting, so that's when I get my PWM out of analog write. But if I write analog write to the analog ports, A0 or A1, I get an analog voltage out, right?
No, that's weird things from the library of the Arduino that they call this analog. Because as I told you, this microcontroller that we use for the 32AP, for example, for the Arduino Uno, the standard Arduino Uno, you cannot output analog signal, only PWM. But with bigger chips or modern chips like the one that we are trying to use, that Neil is always showing these new ones, they might have analog output voltage.
But
so
the Arduino Uno has a thing called analog out. It's got an A0 and an A1. It's got 2 pins that it calls analog out. Are those not analog out pins?
It's analog input only.
Ah, sorry. Yes, those are the input pins, not the outputs. Right.
And there are
sorry.
six pins.
Yeah.
So what we do here is very easy, guys. With this code, we have a for, so it's a loop. What we do is we increase this counter from 0 to 255. So we go to the stand position, to the maximum speed, and then we decrease this from 255 to 0. So we go to from the maximum speed to the lowest speed. So this will increase the speed, reach maximum speed, and then go back to 0. And then we repeat the loop continuously. Sorry, so in this case here, we do this one here. Sorry, at the end, we don't repeat the loop. Sorry, we stop. So we do just once. We go to the maximum speed, and then we go to the minimum speed, and then we stop. So this is the way that you can output a PWM signal. You will see there are many different ways of giving as output a PWM signal. This is one. The other one is to use the servo library from the Arduino directly. Okay, questions about this code, guys? Or question about how to drive a DC motor? Okay, I think we can go on with the next example.
So sorry, yeah, the resistor we have here,
yes,
which is the 2.2 kilo ohm resistor, we can't use the internal pull-up resistor arrangement in the board, right?
You cannot. This is something different because this one, as you can see, is not connected to VCC or ground. It's connected to the gate.
You got me. Yep, got it.
It's just for changing the gate voltage, because maybe this transistor works from 0.5 to 3 volts instead from 0 to 5. So you need to change the voltage. Depends on your transistor you have. So the stepper motors. So here there are some examples about the stepper motors. Again, you need to use a specific driver. I also made a driver if you want. It's open source. It's also displayed in the slide. And so in this case, it's worth to know some basic specifications of the stepper driver interface. So let's have a look briefly to this image. Order, bring to the front. And so this is something standard, honest. So you will find this in all the stepper drivers for all the motors. So if you see here, so on the one side we have the Arduino, on the center we have the stepper driver, on the top we have the power supply, because I remember you need much higher power than the one that the Arduino can give you, and now you have the motor on the right side. So here with these cables close to the microcontroller, we can control the stepper driver. The first cable is called enable. And what this enable does is rather easy. You send a high signal, the motor is enabled. Enabled means that the current is flowing inside the motor and the motor is powered. So if you power the motor, a stepper motor, and you don't send any step to it, the stepper motor will hold position, but will hold position with a lot of force. So this means, guys, that if you try to enable the motor and move the shaft by hand, then, guys, this shaft will not rotate freely. You need a lot of force to actually make it lose the step. So this is the enable. So in machines, typically the enable is used in a way that whenever the machine is not moving, you can disable the motors in a way that you cool down the motors, because if the motor is enabled and the current is passing through it, it will become slightly warm. So you can save a lot of energy by enabling or disabling the motor. You can also think about the Zig laser cutter, for example, that you need to move the axis by hand to take the home position. So what you do is you disable the motors and then you can move the motors by hand. So you can think about like inspection or calibration and so on. So then you have two other pins. One pin is the step pin, the step connection here, and the other one is direction. So direction works in a similar way of enable. So it can only receive signal high or signal low. And if it receives signal high, for example, it rotates clockwise. If it receives signal low, it rotates counterclockwise. So this defines the direction of the turning of the stepper motor. In this case, guys, enable and direction really are depending on the stepper driver. So not always high means enabled or rotate clockwise. Maybe low means rotate clockwise in other drivers. William.
The step line.
Yeah.
Sorry, I had a bit of a brain fart. Is that we're going to put every time we send that a plus, we're going to move by a step, or is that somehow okay? So that's what it's going to do.
Yeah, actually,
so we just essentially pulse that.
Yes. So the step is the one that takes the famous up or down signal, simple signal, to do one step. Right. So every time we send one wave, we do one step. So the faster you send these waves, the faster you rotate the stepper motor. Of course, if you have the motor disabled, you can send as many steps you want, it will not move. So this is the way that you can control the motor. In these drivers that is not shown here is also present like a sort of trigger. So in my case, it's maybe just so it's easier for you to understand. In my case, this corresponds to these switches. So you have these switches over here that you can move back and forth. And according to how you configure these switches, you configure the stepping mode. So this stepper driver that you see on the screen, and also this one that I showed you before, it's how it's able to drive the motor up to 1/16 micro stepping mode. So if you change these switches, you put them on high or low, you change the stepping mode. From full step, you can go half step, 1/4 step, 1/8 step, and then finally 1/16 step. William.
Okay, I think I'm understanding that. My first question is, what's the capacitor for on your big board?
So the capacitors here, guys, also there are some capacitors in this.
There's some little ones on there.
Yeah, there is also a little one over here. Depends on the size of the driver on the motor and so on. It's using one of the main features of the capacitors, which is like give you a shock of current, give you like a boost of current at the beginning of the start of the motor. So whenever you need to start again the motor, you need maybe a peak of current that the driver cannot give you immediately. So these big caps, they act as buffer, accumulating the charge that is needed to boost the start of the motor every time. Of course, the bigger is the driver, the bigger is the capacitor and so on. You also have other caps, but they are for stabilization of the voltage, for example, of the motor. So the one for stabilization is much smaller than the one that you need to for giving the boost to the motor. So then you variate, as I told you, the stepping mode by changing the switches. So you move the switches, you have to look the manufacturer of the driver, and the manufacturer will tell you, okay, put the switches in this direction instead of the other one. Maybe we can have a look to some of those. One is this one, the other one is the A4988. So please have a look to the data sheets or the configuration of the stepper driver. This is the small one that we were looking before. And if you look down in the specifications, so here maybe it's much clearer. Sometimes you also have additional features, for example, sleep or reset. So you can reset the stepper driver, you can put it to sleep to save energy, and so on. So here it says actually you need 100 microfarad capacitor for the boost. So this means in this driver, this capacitor is outside of the driver itself, is on the board that is hosting it. And then here, according to how to you connect the connection MS1, MS2, and MS3, you have 2-step, half-step, quarter-step, 5-step, 1/60 step, and so on. So these 3 connections are actually here, these 3 here. So if you connect them to ground or VCC, you change the configuration of the stepping mode. William?
Can you explain again, please, how that micro-stepping is controlled? Because inside the motor, there are a series of coils, obviously. And how does the micro-stepping then get below that 1.8?
Yes, so this is rather complex. So the first thing that you have to consider, so let's look this image again, arrange, order, bring to front. Okay. So the first thing that you need to consider is that the signal that you need to give to do one step is always the same. It doesn't change. So it's always this square wave over here. Every time you go from high to low or from low to high, you do one step. William, is this clear?
Okay. Yeah, that far is okay. Yeah.
Okay, then what you need to do half step, you have to divide this, of course, in time. So you divide this in time. For example, you have these lines you see here, and this is divided here. So every of this piece is divided in 2. And then what's happening here is that you don't need anymore the square wave over here. And you know why? Because there is a decay effect. Decay effect means that if you power the coils are going to be still powered for a certain amount of time. They are not going to, like say, the current is not going to go immediately out of them. So it's going to be out completely after this time is passed over here of this wave. But when you subdivide this wave, you still have current. And this current that you have inside the coils is taken into consideration from the driver. So what you do is you still variate these small chops, small, let's say, gaps, small steps over here, but you still take into consideration the amount of current that you have. So this means basically that this is the signal that you send to the motor in reality, but then what the motor will feel is just similar to this one, but in a smaller, very small scale, because when you are close to the peak, you still have this current inside. So you don't go low immediately, but you still have a little bit of current over here. And then the more time it passes, the lower it is. This is logic inside the stepper driver, guys. You don't have to care about this because it's rather complex to generate. So therefore, you don't send anymore high and low, but you don't go immediately to 0 because you still have inside current for it. So you have this kind of wave at the end. So at the beginning, the decay is mixed and then slow. So at the beginning, it drops down fast, and then it's slow after a certain time. Yeah. So it's rather complicated, let's say that. So micro-stepping, guys, again, are useful to give you more resolution in the motors. Some motors, they can change behavior in a way that the more micro-stepping you have, the lower torque you have as output, the lower speed you can reach, depends on the motor. And also, for some motors, you cannot go over a certain amount of micro-stepping. So I remember with some NEMA 24, I tried 1/256 stepping, and this decay was not working at all, and the motor was just like having super weird behavior. So the last thing that you can regulate on the driver from the stepping mode is the current. So you see this little trimmer over here. What you can do is you can rotate this clockwise or counterclockwise to increase the current that you give to the motor. So when you buy a motor, the motor has a certain amount of current that can take per coil. And if you exceed this value, the motor will overheat or will lose steps, will work unreliably. If you have the nominal ampere, the nominal current, you reach the maximum performance. If you have less than the nominal current, then the motor might lose steps if there is a heavy load attached to it. So it will not reach the specified torque. So this stepper driver, A49888, is very common. We have also this in the FabLab if you want to use it. This is the one that I made and works in a similar way, that you have this little trimmer over here to change the current. You can then power the motor with different micro-stepping according to the M1, M2, similar to the other driver configuration. Nowadays, the newest stepper driver, like this one that I love so much, is from a company in Germany, from Hamburg. This chip overrides or improves all these things that I just told you, because in this case, you don't have anymore a physical trimmer to change the current. You can send the current as a digital value, as a signal to the chip. So you can program the chip. Another cool thing is you can change the stepping mode on the fly. So you can have full step mode in some movements and 1/64 stepping mode in some other movements. And this is possible to be done like while the motor is moving, not like the older drivers like mine, where you have to go here manually and change the stepping mode. So you can dig down deep in the datasheet from the stepper drivers and try to find your own stepper driver. So guys, how we can drive a stepper motor from the code perspective? I think this is also rather simple. So what we need to do is to connect these pins that we have. So in this case, for example, enable, step, and direction. And then what we do is we enable or disable the motor. So the enable will be high or low. We set the direction. Direction can be high or low, in this case, clockwise or counterclockwise. And then we generate the famous wave that we were talking to be sent to this motor, to this driver over here, which is just high, then wait 10 milliseconds, then low, and then wait 100 milliseconds, for example, and then repeat this for 200 times. 200 times means we do, for example, in two-step mode, one full rotation of the motor. Guys, questions about this code?
I think the code is pretty clear. We just have to see when we actually try it ourselves, I guess we'll know how it's working. And it'll be the when we add more code to it, how sensitive is the digital write timing here on the high-low, the delay 10 milliseconds here. If we write other things in this loop, like if we're reading a sensor or something, does that influence that?
Yes, of course. So this code that you see here is a very simple example that uses the Arduino libraries, but you're absolutely right, because if you change this time that you have in between the high and low, you change, for example, the speed of the rotation of the motor. So you don't have anymore the achieved speed. Let's say you want to move a 5 millimeter per second, I don't know now the speed, then you change that. Also, if you do this too fast or too slow, the stepper driver has a minimum threshold that you have to keep running, for example, to have a proper step and so on. So you need to be in that range. So the answer to that is that our microcontrollers, they have hardware timers inside. So what you do is you don't anymore wait for 10 milliseconds and then change the signal. What you do is you use these timers, to generate like events or interrupts to have always fixed speed. Think about the CNC controller that EM30 wants to use, like the GRBL firmware, They use hardware timers, interrupts, to make sure that the speed is always the same. So think about, you have 3 motors moving at the same time, plus you need to account for the spindle speed with another signal, So there are several timers that they work in parallel, and because the microcontroller is not really multi-threaded, it can do one task per time. But then with these timers, you can be exact in the timing, these hardware timings. Okay. I think this was the stepper motors. So here there is a simple example, actually 2 examples about the servo motors. Here we just use the small ones that they can be driven directly from the microcontroller. In this case, these often have 3 connections. So you need VCC, ground, and the signal itself. Usually these ones, they work are 5 volts or 6 volts, so they can be run directly and less than 40 milliamps. And then here we can see a little bit of the code. So the right example is the traditional example from the Arduino library, that is the servo library. So you remember that to include a library, you have to do this include statement at the beginning. And then let me bring this to the front, arrange order. Bring to front. Yeah, okay. You have this variable that you declare as a servo type, for example, my servo, and then you have simple functions to utilize the motor. So in this case, you have attach, which means that you define the pin where the servo motor is attached. In this case, pin number 9, and then with the dot write function, you just write the degrees of rotation of the motor. So you move to 0 degrees and then write 1 second, move to 90 degrees, wait another second, and so on. So that's rather simple. In this case, Hannes, when you write this one, my servo.write 0 is like you write 1 millisecond pulse. When you write servo.write 180, you write 2 milliseconds pulse. Actually, we have the possibility to also write directly these numbers by using the microseconds function. William.
I was going to wait for you to finish on that. I'll ask you the question when you're done with what we're just about to say.
Oh yeah, perfect. Okay, so this is like the simple way that the library works, because it's easy to understand the angle of rotation. So you can write the angle directly of the servo motor, and the servo motor will move there, and that's it. The other function that I was talking about is still inside the servo library from the Arduino. Remember always to check the reference, guys. We have this write microseconds, yeah, which takes microseconds as an input value, And this is, again, from 1000 to 2000, as I told you before, which means from 1 milliseconds to 2 milliseconds. And then the way that this works, it's easy. You still have servo dot attach, and then you just run microseconds. And here you have the microseconds. So if you have electronic speed controller, after you enable the electronic speed controller, because also they have a sort of enabling sequence, like the enabling of the stepper motors, then according to how much you send this one, then you move the servo motor, or as fast as the half speed, in this case, for the brushless motor. William.
So my two questions was, the servo motor, you have to, in the example code, you give it a angle to get to, and then you wait a second. So, but that's a guess. You're looking, pi times your thumb as to how long it's going to take for the machine to get to that particular angle. And obviously, if it's a smaller angle, it'll happen more quickly than a second. I mean, if I say write 0 and then I say write 10, I don't need to wait a whole second to go that far. Is there any way to get, I guess I'm answering my own question, but there's not really any way to get any information out of the servo motor as to where it is, right? So I can't write an if, not yet at 10, keep going. There's no way to do that in a servo. I just have to go at its speed, right? And the corollary question to that is there any way to control the speed of the servo motor, or does it just go at its speed?
So I think the answer is negative for this library from the Arduino. You cannot control the speed. It's just by default.
Okay. It goes at the speed it goes.
Yes, it's just defined by the library itself internally, and that's it. And in this case, when you wait here, let me arrange on front. Bring to front. So here you have actually this servo.write. And then, as far as I remember, if I'm not wrong, this should wait that the servo moves in that position. And then you wait 1 second.
Yeah.
Okay, this is
one.
So then this delay is not always 1 second. Here depends on the position that you have currently and where you want to go, how long does it take, and so on. So this is the servo library. But some guys, they made another library, which is called bar speed servo, that builds on top of the servo library from the Arduino, which takes into consideration these things, William. So one thing that you can do here is you can set the speed.
Ah, okay.
Because, I mean, come on, that's normal, no? You want to change the rotation of the servo motor.
I figured there must be a way to do it. I just didn't know how.
So in this case, this library, you can also have this function with the speed, and also you have two different ways of working. One way is you send write, and this will not wait for the servo to move. It will continue to execute the code. The other way is to wait for the servo to finish. So it allows you to finally control this behavior. For example, think about if you want to move 2 servo motors at the same time, or 4 or 5, you need to wait and so on. So what you can do is you can use this library, and I was able to move 5 motors simultaneously. So I made a small robotic arm, that can move simultaneously.
Well, that's going to be important for me, so that's why I was asking.
So with this, I highly recommend this library because it's really good. It's mentioned also in the links, but we can go to it very quickly. Bar speed servo. I've used it. I think they should have a standard Arduino library, to be honest, because it's really powerful library. Actually they changed this. That's nice. So you have moved to 180 degrees, for example, with a speed of 30, and then wait until the move is complete. If you put true here, if you put false, then you have, yes, I will send the link, guys. It's
I was just putting a note there so I can find it later. That's okay. Thanks.
I think it's rather good library.
Okay.
Yeah, here more complex examples with the speed and so on. Yeah.
So this library, as you just said, was when we hit that myservo1.write, that sends the signal to the servo and then says whatever and lets the servo do its own thing. And it doesn't wait for it to come back. But in the other library, in the Arduino standard library, when we write, we say servo.write, it actually hands off control of everything to the servo, and somehow we know that the servo has reached its position. How does the code know to come back?
This one from the servo library, as far as I remember, it should be like this, but I don't know if it's waiting or not. It should be waiting as far as I remember, but I need to check again the specification and so on. Maybe let's look again together. If it's, I call this blocking or non-blocking functions from programming. Servo library. Yeah, here even they don't mention this.
Because I can't see where the return function is back to the Arduino to say I've arrived.
Wait a second. Oh, yeah. Looks like it's blocking, but this is what this guy says. Otherwise, we need to look inside the library, you know, because
yeah, okay.
It's not, but as far as I remember, I mean, it's like this. You write all of this here, you wait for one to finish, then you go to the second one, then to the third one, to the fourth one, you know?
Yeah, but you put a wait milliseconds, right? And so you write, and then you put delay 1,000 milliseconds, then you write, and you say delay 1,000 milliseconds. So the blocking in the code on the right that you've highlighted there, this code, in here you say write 0 and then delay 1,000. So that's saying, go ahead, write. The motor starts moving. I wait a second because that's the longest it could ever take for it to get there. And then I write 90. And then I wait for a second because it could only ever take a second to get there.
But I think
there's no way in here, the Arduino doesn't communicate with the servo to know where it is. There's no position information coming back from a simple servo like this.
No, there is no information feedback coming back from this. Yeah.
So it has no way of knowing where it is.
No, the only way you have to you can know where it is to work again with the interrupts and timers and so on. But this is handled inside from the libraries.
Yeah.
Yeah. So I believe, as this guy says, this library is blocking. Blocking means you write servo.write 0, and you know before this delay, you have to wait that the motor moves there, and then you wait 1 second, something like that. But this library, the library from the Arduino is not mentioning anything about it. So I think this library that solves this issue is the best to work with the sensors. Yeah? So you can.
Well, this one allows you to control the speed, so that's good. That's what I want, is to be able to control the speed. So I'll just use this one, regardless of how the rest of it works.
But also, so William, you have that function that you asked me. So here you can say wait until it finishes to move, or you can just go straight without waiting that finish the move, you know, and move another motor. So you can even control to wait. You can even control the time that you need to wait for a motor to finish the movement or not.
So does this library still working with a 3-wire code with a 3-wire servo though?
Yes, it's exactly working with the same servo, but you can control the waiting. So you can wait for the servo to move or not. You know, so you can move 2 servos simultaneously. So with this, you say move this servo 1 and servo 2 and wait for these 2 motors to finish. So the code will stop in this wait here.
Yeah, okay, but how does that code know that it's finished? How does the information get back from the servo to the main board? There's no input check.
The servo. It's coming from the timers of the microcontroller. It sends enough
microcontroller
pulses or for an amount of time that this library measures inside. So the library measures the time of sending the pulses. You know, it's not the feedback coming back from the servo. It's the library that controls this time.
Okay.
Guys, more questions about the servo? Maybe it's nice to see how the servo, this small servo, is made inside.
Wait, is that just a stepper motor with a gearbox and a feedback controller in it or something? Or
bring to front. It's actually a DC motor with gear and encoders maybe and things here inside to control and everything. Yeah. So some of these can rotate 180, some of these can rotate full rotation. Of course, the big servo I mean, one thing that maybe I didn't mention, the big servos or the advanced stepper server models, they also have a feedback system. So we call this model closed loop control. So they can check if in reality the model has turned or not. And if it has not turned, you know what you can do? You can send more pulses to go back to the position. Let's say that your CNC, it's cutting something very hard, or there is an accident and you lost some step, you know, then the software is able to realize that you lost some steps because some accident or some losing of the positioning of the motors. And then with the software, you can go back to the original position because you can check with a feedback system where you are. So if you open a printer, guys, nowadays, they have these optical encoders on the back of the motor that they can check the position. I don't know if you ever saw these optical, they're just discs, encoders. They're just discs, guys, with a sort of, you know, they are open or closed, and they can count the number of discs that you have moved, for example. So this is a very complex one, but you can have simple ones. You can even do it with the laser cutter or the varnish cutter. You have a disc with stripes, black and white, you know, and then you can make it.
Extra credit from Neil.
One thing that is worth to mention, guys, the most advanced stepper drivers, they can also measure the status of the motor according to the current. As I told you, for your DPV harness, I think in one of the last meetings, and they can detect if the motor has lost steps, for example, but they are not so precise as the encoder, of course, if the motor has lost steps. Okay, guys, more questions for the servo motor?
Did I remember seeing like a 4-wire servo motor?
It can
So
be
the 3-wire is the standard one. Is there such a thing? Am I remembering that right? That there's one that also has a 4th wire with a signal in it? Can that be?
It can be the one with the feedback.
Okay.
Yes. So guys, we go to the brushless motor now. So the brushless motor is called like this again because it doesn't have any brush inside. Here we can see a little bit of a schema about how this motor is made, arrange, order, yeah. And so in this case, these motors never have different configuration. So the starter that stays inside contains the coils that will become an electromagnet according to the flowing of the current. And on the outside, you have these magnets. One difference is these magnets are very strong magnets, like the one that you have in the hard drives, like neodymium magnets. And again, you can see that there are no brushes that touches the stator with the case or the stator with the rotor. And the motor construction itself, it's rather strong. It's made out of this, like usually aluminum frame. And the other thing that you might notice is that the part that rotates here in this case, it can be like the outer case. So if it's the outer case that rotates, these are called outrunner motors. Like it's the case of this motor that you see in camera, where the outer case like rotates. Yeah, then you have a couple of bearings, one bearing here, and then a clip to keep the whole construction of the shaft inside the motor. So the way that we can control this this motor is totally similar to the servo motor. In this case, we would like to use the microseconds way of moving the servo motor, so we can write the directly the pulses in it and decide the speed. So if we have maybe a small look to this code, I think there are two examples here. So one way is just using the write here, but then in the write is hidden these microsecond pulses because they are from 0 to 180. So it's not so clear where are you moving. But then the way that you control it is exactly the same as the servo. You attach it. You need to send a pre-command, a specific command to electronic speed controller to, we call it arm it, to enable it to work. It is done here in the setup. And then you just write here servo.write 55, you write just here a value, and that's it. So this is the way that you do it with the write function of the servo library. And this is the way that you do it with the microseconds. That's much more clear. So you attach the motor to a specific pin, then you write 1000, and then in this case, you map this from the reading from a potentiometer with the analog read, and then according to the potentiometer, you use the map function to convert this to a value between 1000 and 2000 from the analog read, which can vary from 0 to 1023. And then this writes x.write microseconds value here inside the writes the value inside the motor speed controller, the electronic speed controller. So it's like having an op controlling the motor directly. I think, Hannes, have you thought about a way of controlling your motor? Should be only on and off, or should vary the speed somehow?
Yeah, I changed my plans a bit. So I was going for 2 switches. First, my idea was to have 50% of the maximum speed and 100%. But now I just want to use one switch as the trigger, and the other one is to rotate between the different speeds. So that I just go up in 25% steps, for example. So I go with 25%, 50, 75, and 100, for example.
I see. Just make sure that you have also some kind of, as we were discussing, even not in emergency only, just safety mechanism to go quickly to 0. So if you increment every time you push, you need to push 3 times to go to 0, maybe.
No. I just, it's like a gearbox in a car. So I use one switch to rotate between the speeds, and the other switch, pressing the other switch is like letting go of the clutch. So engage or disengage with one switch, and the other one just goes through the different speeds and then back to the lowest one again. And the other one just motor on, motor off.
I think it's very similar to what Carsten did. But then the question is, what will happen in case you are, let's say, a 75% speed with the clutch activated, and then you deactivate the clutch and you reactivate the clutch. You go to 75 back, and you go back to 0.
75.
I see. Okay.
Wait, what did you just achieve?
I'm just imagining my diver propulsion vehicle on at 75%. And I stop it, and then I grab it and start it again. It's going to leave without me.
Yeah,
I was just going to say, what you might do with your second button is make it a read switch, so that something in your hand, and when you second button, if your hand lets go of the machine, that it stops.
Yeah, no, the second is of course it has to start slowly and then increase the speed up to 75% again, or to the last speed up.
Okay, so I'm gonna go as opposed to.
Yeah, it was, Florian told me the story of a diver who called his DPV a und weg scooter because. Pardon?
That's the kind of name I would expect. Yes.
Yeah. So he was imagining the scooter to be like, if he hits the trigger, he's gone. The other divers don't see him anymore. But the trim of the scooter, or the buoyancy of the scooter, wasn't right, so it was too heavy, and the scooter fell off the boat and was gone. He didn't find it anymore. So the other people on the boat just made fun of it and kept on calling it the und weg scooter.
I think this happened to Carsten also because we had the same, that he was going back to the previous speed. after engaging and disengaging it, you know.
Okay.
Yeah. So what we did now in this case was that every time that he disengaged the motor,
Yeah.
starts back from 0.
Yeah.
But not going back to 75 slowly. It starts directly back from 0. So you need to, again, keep pushing. Yeah. You can think about it later on.
Yeah.
Guys, sorry, I was muted.
Oh, I thought it was me.
Oh, man, I said a lot of things. So this is the way that you can connect the motor speed, the electronic speed controller to the microcontroller to the motor. So
That's the disadvantage of your pollen protection. We don't see when you're talking.
I have to watch this after this lecture because it's going, yeah. So you have the motor here that connects through these cables to the electronic speed controller. These cables, guys, are these 3 different signals that have to go to the coils. And as an effect of swapping them or changing the connection, is that the motor will rotate in the opposite direction. So you can rotate clockwise or counterclockwise just by changing the direction of this wires over here. Usually in the drone ones, like this one that you see in the camera, they all have the same colors because they are not like having any direction. So then from the other side of the motor controller, you have the battery that connects to the motor controller with positive and negative. In this case, we are talking about, of course, much higher voltage than the one the microcontroller takes. And then from the microcontroller side, you have the ground that needs to be shared and the pulse width modulation signal that connects to the electronic speed controller. This small red cable here that is not connected, it can be the integrated step-down voltage regulator that can be handy to power your microcontroller because it usually gives you back 5 volts. So you can power everything from the battery without the needing of having another battery or another power supply. The electronic speed controller, guys, they will take a lot of current. And for example, also the LiPo battery, they can give you, in a very short amount of time, a lot of current. What you need to be really cautious with, apart from the power from the motor itself, that can, of course, chop your fingers in case of the propeller, is that these traces or these wires are properly dimensioned. So you know that the more is the cross section of the wire, the more current it can flow through it. In my case, this was critical. In my final project, I slightly under-dimensioned these traces that they go from the battery to the motor speed controller. And what happened is that the trace exploded while the drone was flying. So the drone, guys, was just like going crazy and like falling down almost immediately. So in your case, I don't know how is the dissipation, your DPV, but you need to dimension this really carefully. Also, they can become very hot before exploding. So this is the electronic speed controller. For the motors, what you can do is before you buy them, you can look the specifications. In this case, these ones are for drones, but honest, you can find similar ones for the for the water. In this case, the one of the specs of the brushless motor for the drones is this KV. It's actually a common of all the brushless motors. Also the one for
RPM per volt.
Perfect. It's 1000 RPMs per volts or RPMs per volts. In this case, 820 means that every volt you have 820 rotations per minute. So if you have 10 volts, you have 8,200 and so on. So this table shows you that the manufacturer tried the motor with different propeller, because you know that according to the load, this motor can take different amount of current. Therefore, you might need different kind of batteries and so on. So the propeller, this is more about the drones and more about the DPV. You know, propeller have diameter and pitch. So the diameter is just the sides of the wing. The pitch is the inclination. So how much distance you cover with one full rotation inside like ideal fluid. So of course, the more is the pitch, you know, the more water, the more air you move per rotation. Therefore, you need more torque. Therefore, you need more current. But then according to this, then you need different battery. You achieve different RPMs and you achieve different thrust, for example. So here you see the same motor, you have different voltage, same propeller. It takes more or less current. It gives you a thrust here in grams and consumes a specific amount of power. It has a specific efficiency. It can reach specific amount of RPMs. So this, Hannes, will depend on your props that you have and the density of the water of the sea that you need to push through. Usually, the motor that have higher KV are the one used in small drones, so they have a smaller form factor. So the smaller the motor, usually the faster they can spin. The bigger the motor, usually the more torque you have. So the larger propeller you can fit into it. Of course, for the propeller, it's important also to define the number of wings you have. So usually in the drone propeller, you have 2 blades. Maybe in the DPV, you have 3 or 4 or 5. Every time that you add 1 wing, you add the need of having more torque, you need more current, and so on. So you will move more water or you will cover more distance and so on. Okay, so guys, this is maybe a little bit of inside of our electronic speed controller. And as you can see, it's rather complex circuit. William?
Yeah, just a statement. I have a book in my office when we can get back there called the Propeller Handbook. So for Hannes, if you come to designing your prop and you need to look at the power requirements for an underwater propeller, we have some material in the lab you can use to specify the prop and the power you're going to need on the shaft.
That would be awesome. I just read the email from, at least from our dean of our faculty. Looks like we can get back into our offices from Monday on. And,
same ours. You need in Cleves. You need permission from the dean. So we'll figure that one out when the time comes.
Okay. Thanks.
This comes back to another topic that is also different brushless motors are made for different purposes. Like the one that are made for the drones, guys, are not really good to have a lot of torque since the start of the motor. So we might need to look to a specific made brushless motor. So here we have the electronic speed controller. This in the center is a microcontroller. These 2 are MOSFETs, and you also have MOSFETs on the other side. And what it does, basically, it takes the PWM signal here as an input, and then through the microcontroller and the usage of the MOSFET, these caps and so on, it gives the proper power signals to the motor to move. So it's rather complex object. The microcontroller itself runs a specific software onto it to manage the signal for the specific motors, to keep the timings correct and so on. The new ones, they have 32-bit microcontroller, a very advanced software on it to specifically manage the motor that need to move. Okay, I think just one side note is one day I would love to make a brushless motor with a lathe because the big ones looks rather simple to be made, and I would like to copy one of the big Chinese ones. Could be cool to have an open source brushless motor. Okay, I think we finished with the motors. If you don't have any other question to them, we can go a little bit to the displays. I think I was showing you this display in the input device is the same that Harley was using. This is a character display. The character display is the simplest display you can use for your microcontroller. And it's called like this because it can only display characters. So if you see the image of this display, and you see here this small rectangle, basically these rectangles are like the single slots, the single space for each character. And when you buy this display, the specification is given by the amount of character that they can show. So in this case, this is a 16 times 2 display. So this means every row, it has 16 slots, and you have 2 rows. Questions? No, okay. So this display over here, it can come with a backpack chip, we call it. So this means you have a chip, a microcontroller or a controller on the backside, and use serial or I2C communication to work. The standard one doesn't have these connections and this microcontroller on board, and it uses a lot of connections to work. You can see here in this image, it really wastes a lot of connection. I really advise guys to use this display if you need to do something simple, especially if you have the one with the backpack. Is, for instance, sometimes used in some simple open source 3D printers, or to just show like really small amount of data. Here you control it directly. You just need to connect a lot of digital pins to the display. You also have a trimmer that is sometime on the display, sometime outside, to control the contrast of the display. And then you might also have a backlight on the display itself. Sometimes yes, sometimes not. If you have the backlight, you can power the backlight usually with 5 volts, or you maybe need 3.3 volts. This depends on the specification of the display. You have in fact here a resistor to change the voltage. So we are lucky because in the Arduino we have also a library to manage the display. It's called the Liquid Crystal library. And what it does is it takes as an input where you initialize it, the pins that you need to use to connect the display to the microcontroller. And then you initialize the display according to the shape of the slots. So you have 16 times 2 display. And then you just print directly, for example, hello world. Or you can set the cursor. The cursor, guys, is the same as the cursor that you have in Word or you have in any text editor software that you position where you want to write. So you position the cursor in the slot 0, row number 1, and then you write, for example, the milliseconds here. And this, it's, I don't know, 5171, for example. And that's it. This is rather easy to use display. I think, guys, the display is rather pin consuming. I really recommend it for some tests, or to have one with a backpack chip that can work with less connections. Do you have questions about the display? Okay. I think the other example that we have here is the graphic display. I like so much this kind of display because it can display not only characters, but you can put graphics on it. This one is 128 times 64 pixels. One example here, maybe. Yeah, there is one example. You can throw anything you want on it. In this case, this means you can control every pixel. But the cool thing is you also have a library that you can use to draw, for example, circles, or to draw lines, or to draw rectangle, or to draw character with different fonts, and so on. So you have sort of graphic library for it. And this one has a chip on the backside, and that needs only 3 digital pins to interface it with the microcontroller. So it's going to be to control it. The library that you can use is this U8 glib.h. It's rather very powerful library. And then it's compatible with a lot of displays. And here is a link of it. And this shows you all the examples and the things that you can use, your phones and so on. It's really widely used library. We can go to the wiki here. But maybe front string angling, maybe. So this is the size of the display, 128 times 64. Here you can work with the dimension of the character or of the things that you want. You can set the font, for example, over here, define the pixel of the height and so on. It's really easy and simple to use here. You can even define the width of a string and so on. Let me check if I can find some graphics example. Here there is the reference manual. Look, you have this nice primitive like draw box, draw circle, draw disk, ellipse, frame, lines, pixels, and so on. So you can have like your own graphics to it. You can even, guys, display PNG or a bitmap, let's say, black and white, of course, with pixels and so on. Yeah, I think. So you have also the backlight over here that can be powered. You can see a backlight maybe on the screen. Very nice to see. Some of my students, they made some video games with this display in the past. The fundamentals. And the refresh is also not so low. Question? Okay, guys, that's it. I'm sorry that I didn't put many displays in it, just simple displays. But more or less, they are quite similar to the other ones that you can use. Especially this last one, this library, this U8G, it also works for displays with colors and with graphics. I will send you the link now in Skype. Oh, Kai left the lecture.
I linked this document in the, or is it this one? This is the link to the slides? No.
The link to the
sorry.
slide, I will send you now.
It's in the wiki already.
Okay.
But I'm not sure if everybody has access because it's not public.
Oh, I'm really sorry. Let me put it public.
But just in case, you could ask for permission, or we make it public.
Sorry.
I have a few how to say notes. Do you still have enough energy for 5 minutes?
Yes.
Yeah. Okay. So I will quickly share my screen. Can you see me?
Yeah.
Yes.
Yeah? Okay. So let's start at the beginning. Okay, so Kai was asking something about saying something like, oh, what is a servo good for if it just makes one turn? First of all, there's like one turn and multiple turn servos, but that's actually, the point is that a servo is not a type of motor, but rather a type of control. You could turn any motor into a servo motor just by attaching a way that it measures its position. And there's commonly two different types of measuring the position, digital and analog. So people talk about digital servos and analog servos. In the case of an analog servo, it would just be like a variable resistor. Can you see my cursor? Yeah? Yeah? I don't see you nodding. Okay. So this is like the little board that is inside one of those small servos. And the shaft of the motor just goes through this little potentiometer. And this way, from the resistance, it can know where it is. And this way, according to the PWM that you send it, it goes like forth or back until it reaches. There's a little controller in here that goes forth and back until it gets to the position that you sent it to. The slightly more complicated servos are the digital servos. And they have something like this built in. which is an encoder disk, very similar to what Daniele showed, like a little transparent disk with like holes. So on one side you have a light, and on the other side a light sensor. And this way you can know if it's turning and in which direction. And there's two different types, absolute ones, which is those. So you need one LDR LED for each of those rings. And then you can actually know where exactly it is. You don't need to count the steps, but you can actually say now it's at 45 degrees, for example. And yeah, I make it short. If you are interested, I can explain this in more detail. And then there's those incremental ones that are just like a stepper motor. It only knows I moved a bit in this direction, forth or back. This is by having those two rings, a bit coarser or a bit finer. And so there's like absolute servos and relative servos. But servo is actually anything that is moving and measuring its position. So you also have linear encoder. So for example, for big milling machines, you have a glass rail at the side that sometimes is optical, like the one up here. Sometimes it's magnetic, like the one in your caliper, you know, for measuring distances. And they're usually out of glass, so they don't expand when the machine heats up. And in this way, your servo is basically the whole thing from your maybe DC motor that moves it over the glass ruler, over the controller, back in the loop. And the whole thing is called a servo, even though it's actually 4 different things. And a servo can have a DC motor or a stepper motor or a brushless DC motor. So it's not the type that makes it a servo, it's the controller that makes it a servo. So here, for example, you have a stepper motor with electronics attached, where there's a integrated digital encoder. And this makes it a servo, even though it's a stepper motor. And here's different types of absolute and incremental linear encoders. So it gets pretty complicated pretty fast. But this is kind of industry standard. So whichever big industrial machine you have, they have glass rulers, and they all run on servos. Mostly with
one question about the stepper motor as a servo.
Yeah.
But you then have to stick to the steps, right?
Yeah.
Okay.
You can't do like in between the steps thingies. Well, it's kind of like the micro stepping. You kind of could go in between, but more difficult. Okay, but actually the motor that runs our world is the 3-phase induction motor. So this is the most common motor that is put almost anywhere, like ranging from so it's also a brushless motor, so it has no brushes. And it looks very similar to a brushless DC motor, but instead of having the magnets on the rotor or on the stator, it's an induction motor. So it induces a current in some aluminum stripes that are on the motor. Yeah, those are used anywhere from like those big trucks to, this is the one from the ICE or from the S-Bahn. It's like the most produced motor in the world, and in order to adjust its speed and everything, you use what is called a variable frequency drive, which is a little box that generates like a custom, like if you run one of those on regular AC, it runs at a constant speed because you have the 50 hertz and the 3 phases, and this is how most of them run. So they run at 1,500 something rotations. And if you want to adjust the speed, you have to generate your own 3-phase current where you can control the frequency. And for example, if you buy like a spindle for a milling machine, it already comes with a VFD, and then you can very comfortably adjust what this thing is doing. Yeah?
But is this also happening for the brushless models, of course? The small one?
The small ones, it's kind of similar, but the BLDCs usually have magnets, whereas the three-phase induction motors don't have magnets.
Are the motors from the spindle synchronous three-phase or asynchronous?
They're asynchronous three-phase induction motors.
Asynchronous, okay.
Yeah. Or maybe I mixed it up. Like it's asynchronous.
From what I remember, synchronous is like that the magnetic fields, the rotation of the magnetic fields, has the same speed as the rotor.
Exactly. Yeah.
Asynchronous is when there is a difference.
A difference. Yeah. Yeah. I always mix it, but I can quickly look it up. And so. Yeah, then one topic that Neil always skips is the piezo motors that I think are very interesting. This is like the Festool Ant, which has like a 300-volt circuit for running those tiny piezo motors. Like I would be really interested in getting into this if somebody's interested. They can be super tiny and very powerful. And yeah, for the BLDC drivers, like the usual, because William was asking what the PWM frequency is. So if you Google for it, it says it's usually constant at bigger than 10 kilohertz. Whereas the standard servo PWM frequency is between 40 to 200 hertz. So for example, right now I was fixing the little milling machine from Ahmed. And it has a brushless DC motor. The problem is that the standard library for Arduino is outputting the spindle control at the standard PWM frequency of Arduino, which is 976 hertz on Arduino, which is a bit too fast for controlling the. It's great for controlling an H-bridge or for controlling a DC motor, but it's too fast for the BLDC driver, for the ESC. And so if you are on the right pin, because there's like several pins that you could use, you can try to get it down up to 61 hertz, but it's still a lot higher than the 10. No, it's a lot higher than the 40. Well, it's somewhere in the 40 to 200 hertz. And depending on the ESC you're using, this might work or not. In my case, it doesn't. So I made an extra little circuit. Yeah. And so the PWM frequency of the Arduino can go from quite low. I think for my Fab Academy, I actually measured it. And it went from like once you want to go into the higher PWM frequencies, you have to program it in C. Like this is a bit of the code that where you set your registers. And by default, it was at 500 hertz. Oh no, first it was at 50 hertz. Then if you burn the bootloader, it goes up to 500. And then with some programming, you can get it up to 32 kilohertz on the ATtiny. And on the ATmega, it goes up to 8 megahertz, but I also read 16 megahertz somewhere. So that's a matter of configuring your Arduino. And yeah, that's basically it.
Yes, you have to briefly excuse me because at 5:30 I have to give the other lecture for the other students.
Okay.
I think
we're done. Yeah. Maybe one more little thing. If you're into like the guys from Open Source Ecology, they're building their own brushless DC motor. If you have a look at this page, it's an open source self-printed BLDC motor, which is an interesting project. Maybe it's easier to buy one, but they want to revolutionize the market for electric drills, which is dominated by 3 companies, and they want to make their own. Okay, I can.
Fun stuff. Thank you both for the excellent lecture.
Yes, thanks.
Now we got to go.
If someone is interested in Eber's tail, William, you should take 20 milligram, not 10. If you take 10s, it doesn't work so good than 20 milligrams. The doctor said to me, if you take twice 10, it will not work. You have to take 20 milligram.
Okay, I'll look into it.
Okay, cool.
Great, thanks, guys.
Yes.
I need to get off the computer because my eyes are going square. So we'll see.
Okay.
Bye.
Bye.
Bye.